The moon is made of material from the Earth and not from Theia. A new NASA study finds, this is a recent study, February 5th, on Extreme Tech by Joel Hruska. It's estimated that some 4.5 billion years ago, a Mars-sized rock is theorized to have collided with Earth, proto-Earth. And this collision is one of the only ways to create an Earth-Moon system with the properties we observe today, and it's also could have been partly liquefied Earth's surface, destroyed Chaosian property values, and created an atmosphere of plasma metal vapor around both our planet and the enormous cloud of angry debris that surrounded it. Of course, the debris coming from this huge crash. But there have always been some unresolved issues with the giant impact hypothesis, hereafter abbreviated GIH. The chief problem is in answering the question of what happened to Theia, the Mars-sized impactor that supposedly struck our planet, named for the mother of Selene, the moon goddess in Greek Selene mythology. In the conventional explanation of the giant impact hypothesis, GIH, the material from Theia becomes the basis for much of the moon, mixed with some material from Earth. But the problem is some of the evidence points in both directions. The oxygen isotopic ratio found on the moon is essentially identical to Earth. Oxygen isotope ratios, which we can measure with great precision, are different for each body in the solar system. The only reason for the Earth and Moon to align in the way they do is if they are made from the same stuff. But if the Moon is made from an impactor, as theorized, the ratios of siderophile elements, that means metal-loving elements, should be different than they are. And specifically, we should find more of them than we practically do. A new paper from planetary scientist Kevin Ryder of the Astromaterials Research and Exploration Science Division ARIS at NASA challenges the idea that the moon formed principally from Theia. Ryder built a model to compare the concentrations of 14 specific siderophile elements in the final Earth-Moon system by controlling various aspects of the initial collision based on what we know about the moon today. Ultimately, the model in which the bulk of the moon's material came from Earth is a much better fit for the disposition of siderophile elements that we see today than any theorized model in which the moon is mostly composed of the likely ingredients, quote-unquote, of Theia. And this is the NASA video showing the evolution of the moon's surface in our best current understanding from after its initial formation until the present day. Researchers have analyzed small subsets of these elements in the past, but this is the first time that all 14 elements are modeled together to analyze the Earth-Moon system, Ryder said. And he explains, by simulating the main processes contributing to the moon's formation and early differentiation, we're able to predict the level of each element that should be present in the moon's mantle. Ryder then compared his model to the actual moon rocks found by the Apollo astronauts and found a strong match for 9 of the 14 volatile siderophile found on the rock samples. In the case of the other 5, Ryder believes they may have migrated out of the gas cloud created by the initial impact and dissipated away from the system, or Theia, explaining why the moon is more deficient in these materials than it ought to be. One of the problems with reconciling these differences is that it's rather difficult to provide enough energy or completely liquefy and remix rock in a homogeneous way. This is where the molten rock atmosphere idea I referred to earlier comes in. One theory to explain the similarities in composition between Earth and the Moon, dating back to 2007, is that a common plasma metal vapor metal atmosphere may have formed between the two bodies post-impact, mixing them together and resulting in the configuration we see today. Ultimately, this seems like the kind of problem that could be substantially illuminated by a deeper exploration of the lunar geology. There are fundamental questions about whether or not the moon rocks retrieved by the Apollo astronauts represent an accurate picture of the moon's geological history. While NASA deliberately chose landing sites at different craters and areas in an attempt to retrieve rock samples that would reflect different points in time, later research has suggested the impact that created the Imbrium Basin might have been large enough to deposit debris at all of the sites the original Apollo astronauts visited. Instead of sampling rocks from throughout the moon's history, we may have only sampled the same event. Now, even if that's true, it wouldn't mean that the GIH is false. No other theory for how the moon could have formed addresses as any peculiarities and problems in the Earth-Moon system as the GIH does, and no option is as broadly supported. But additional data points gathered from beneath the lunar surface or from areas where the Imbrium impact could not have thrown debris could shed considerable light on this subject. The astronauts of Apollo 14 may have found pieces of Earth lying on the moon then. This is by Joel Hrushka on Extreme Tech. Continuing, Apollo missions may have been launched as part of the Cold War era race with the Soviet Union, but the geological knowledge we gleaned from them was considerable. Until Apollo, we didn't know that the Earth and the Moon appeared to have similar ratios of atomic isotopes locked within their respective rocks, suggesting they formed from the same base material. But Apollo 14 astronauts may have brought back something even more extraordinary than the lunar rocks they thought they were collecting. A new geological analysis published on Earth and Planetary Science Letter suggests that one of the lunar rock samples the astronaut returned contained a rock sample that, as we said, originated on Earth. So basically it was an Earth rock. This is a lunar sample, 14321, known as the Big Bertha. The Lunar and Planetary Institute, which has an extensive set of slides and cross-sections of LS 14321 on file and available, writes, largest sample returned during Apollo 14 mission is known as the Big Bertha. This sample is the third largest sample returned by the Apollo mission. This breccia was collected during the second EVA at Station C1 near the rim of Cone Crater. This large sample is typically of the apparently dominant rock type in the Cone Crater, ejecta blanket. It's moderately well inubriated breccia, in which predominantly dark clasts are set in a lighter matrix. This rock contains a 2-gram felsite clast. With quartz, feldspar, and zircon embedded with it. These are all uncommon elements in lunar rocks, but common in terrestrial samples. The chemical analysis of the fragment also appears to demonstrate that it formed under conditions analogous to those found on Earth rather than within the Moon. And, quote, what we did was use the composition of minerals in the fragment to show it formed under conditions that only occur on Earth, end quote. Robinson told Gizmodo, quote, for example, the composition of certain minerals are sensitive to temperature and pressure. They contain more or less various elements. They crystallize in hot or cold, deep or shallow environments. Other minerals can indicate if the rock formed in the presence of lots of oxygen or in a very oxygen-poor environment. Our data shows that this fragment formed in a high-pressure, more oxygen-rich, and lower temperature environment than occurs on the Moon. Essentially, you had to have come from an Earth-like environment, end quote. The paper lays out somewhat more detail, but the basic conclusion is the same. Either this fragment of rock formed under high, unusual conditions within the Moon, or it represents a bit of Earth flung heavenward as a result of a meteorite impact. Later lunar impacts and geological events resulted in a bit of Earth rock being embedded in a larger sample of a more typical Moon rock. This is less fanciful than one might think. The rock sample is an estimated 4 to 4.1 billion years old, from a time when the moon was much closer to our own planet. It's entirely possible that massive meteor strikes from early in our own history delivered significant amounts of material to the moon in earlier epochs. The complete lack of erosion on the moon's surface may also have helped to preserve samples of this time period. The oldest defined date rocks on Earth have been dated to approximately this epoch, though there is some uncertainty in the exact age of such ancient samples. In theory, it wasn't proven, and there have been some skeptics who have argued that the lunar impact could have created the rocks in question, but it's also possible that Apollo 14 astronauts brought back a tiny fragment of something even more remarkable than they knew. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.